So this is part two of the dissolved oxygen presentation, and this is going based off of the order that's listed on YouTube. So let's get started. So we have for our dissolved oxygen and temperature, the temperature is pretty much the parameter that most directly affects dissolved oxygen that's in a waterway. The higher the temperature, that also means the lower the amount of dissolved oxygen that's in that waterway. A great picture in your mind to think about when it comes to the relationship between temperature and oxygen is think about a pot of water that you're bringing to a boil, right? So let's say you have your pot of water, you've turned your burner on, and as that water starts heating up, of course, water vapor starts to form, where water turns from liquid to a gas, but you also do have oxygen that's already trapped in that water evaporating into the air, and that starts to happen more and more and more and more. So the same logic applies to a waterway, where during the summertime, for example, when it's nice and hot outside, it's heating the top surface of that water. Therefore, it causes the dissolved oxygen that could be closer to the surface of that water to evaporate up into the atmosphere. And then the opposite is true, right? So the lower the temperature, the higher the concentration of dissolved oxygen. So if you were to go out into the field and take the top temperature of the, not only the temperature, but also the amount of oxygen that's in that waterway in the summertime, compare it to the wintertime, you will find in general that the dissolved oxygen is higher in the wintertime. So we have our charts here, and you'll notice that it is dissolved oxygen content versus the temperature, and that the temperature is in degrees Celsius, dissolved oxygen is in milligrams per liter. Just as a reminder, milligrams per liter, one of them is equivalent or the same as 1 parts per million. And the thing that you will of course notice is that for our seawater, the amount of dissolved oxygen can top out at about just under 12, and it will decrease as the temperature increases to about just below 6 parts per million, versus fresh water, where the dissolved oxygen tops out at 14, and that the amount it tends to lower to, although it can actually get lower than this, and the same holds true for seawater, it can decrease to say about 6 parts per million or 6 milligrams per liter. So notice the difference in terms of not only how much oxygen this water body can hold, but also the change, right? So you'll notice, and I'll change colors here, you'll notice that for a freshwater system, the slope of the amount of, as the temperature increases, the slope is much higher compared to, or much more steep rather, compared to the drop in dissolved oxygen concentration in a freshwater system. And that trend tends to continue, does start to level off as you get closer and closer to the bottom portion of the concentration as the temperature increases. However, especially initially, that temperature does drop in terms of freshwater. And it makes sense. It's the same analogy if we go back to our pot of boiling water. A lot of people do like to add salt to their water as they're boiling pasta or making rice. And yes, part of that is for flavor, but the bigger reason is because it does make your food cook a little bit faster, right? And the reason for that is that when you add salt to that water, salt increases the boiling point. So instead of it being 100 degrees Celsius, it's actually higher than that. And that's actually a good thing, right? When you have water in general that's boiling, there's energy that is being released, right? Versus if you have a higher boiling point because you've added that salt, a lot of that energy still gets trapped or stays within that water. So because it stays in the water longer, that energy transfers over to the food to then cook your food faster. So other water quality parameters, I mentioned salinity. We did talk about the relationship between salinity and dissolved oxygen, and I already mentioned the reason why. Just to go into a little bit more detail, the reason for the increase in the boiling point is because you do have extra ions that are in that water. Those ions, remember, they break apart because the ionic bond is weaker. It's weaker than a covalent bond. So once that salt is in an aqueous solution, it dissolves and ends up floating around as ions. And the interaction between the sodium, the chloride, and then the water molecules itself, that increases because of those interactions. It needs more energy to disrupt those brief connections that they all make in that water. And because of that, that's what ends up causing your food to cook faster. Or in the case of a waterway, that makes it so that the water, if it's seawater or even brackish water, and by the way, the brackish water part of this graph is this section right here in the middle. And as a reminder, the salinity of brackish water system tends to be between, it's a big range. It can be between 5 to 25 parts per million. It tends to stay closer to the 5 range, but it can go up as high as 25 parts, actually parts per thousand, excuse me. So that part right there, it again shows you that there is a relationship between dissolved oxygen and salinity. So stratification, right? We talked about before that stratification does occur in nitrogen systems, in phosphorus systems, and now, of course, with dissolved oxygen. Yes. So the line that actually separates the different, or that separates the layers of your water column here, it is called a thermocline, which is what you see here. Forgive me for that squiggly line. It's not the best, but that's okay. So you'll notice that not only the color change has more to do with the amount of light that's penetrating the waterway, but in this case, it also is to distinguish it between the different layers of this waterway. So you'll notice in this top portion, depending on the amount of wind that is brushing along the top of this water, that can cause mixing. And you'll notice here at the bottom half of this water, there's not quite as much, if any, mixing at all. And that just depends a lot on the depth. It depends on if there's other organisms that could be swimming in that water that could then disrupt or cause internal currents within in that water. But in general, if there's nothing else there, then most likely the mixing will happen at the closer to the surface of that waterway. Just a quick note, what that also means too is that the amount of dissolved oxygen is also going to vary depending on the level of mixing, right? So we have our winds, as we pointed out before, and with that wind, it will also cause the amount of dissolved oxygen to circulate. The 100% that you're seeing here, that's referring to something called the oxygen saturation. We didn't talk about that during our lecture, but it just essentially means how much air can you actually pack into that water. And in this example, it's at 100%. What's really interesting as a side note is that it can actually go beyond 100%. That's called supersaturation. It doesn't happen very often, but it is something that does occur. Whereas the section of our layer that does not have quite as much mixing, it is at about 60% saturation. Just means there's less dissolved oxygen. Again, this also depends on temperature, which is what we talked about before, right? So here you see thermocline is the dividing line between each temperature layer. The temperature is what's affecting it. So in this example, most likely this is occurring in the wintertime. Referring again back to the slide where we talked about the difference between the amount of dissolved oxygen in a hot environment versus a cold environment. If this was the summertime, it would probably actually be the opposite. The dissolved oxygen would sink to the bottom, and whatever has stayed on the top, it would actually evaporate up into the atmosphere during the summertime.